Okay, from your feedback, a few of you asked me, like you said you were confused by the null distribution and what that is. So I want to show you some data. I feel like sometimes when we look at something that we don't think is relevant, that it's harder to understand, why somebody's doing something. So the first thing is that what is a distribution? In your book, they kind of say it's the pattern of the data. So I don't know, does anybody have a Garmin? If you're a data nerd, you'll love Garmins. Like these thingies that give you tracking. I don't know what the Fitbits look like, the output from Fitbits. How many of you have a Fitbit? So Fitbit is like a little bit more popular, but I don't know what kind of output you have from the Fitbit. I actually looked at different devices and I said, okay, this is the one I want because of the data they give me. So one of the things it gives me, it gives me a distribution of where all Garmin users are for steps per day. So this is steps per day. They say steps, the actual label is steps per day. Because how are you going to do steps? You have to corral it somehow. Steps per day makes it a rate 104. So this middle part of this curve, this shape here that you're looking at is about 8,500 steps per day. So this is Garmin users quite a bit. It's a representation of maybe people who buy these kind of devices. So it's giving a good rep sample, actually. So the x-axis always have whatever you're measuring. So in this case, I'm measuring steps per day. So that's the x-axis, whatever you're quantifying. The y-axis has the frequency of people that are doing that. In this case, what they did is they have it as percents. So this axis here would be how frequently in your sample you see something. So if you're flipping the coin, would you think that it'd be frequent to get 9 out of 10 flips heads? No, so you'd see a little bump for that. It could happen. You could get 9 out of 10 heads, but it's probably not frequently happening. What you'd expect to see, the frequent happening is what happens the most. So that's what they're calling the center. So if you look at it, the center kind of looks like 8,500 steps per day. How many of you heard the 10,000 steps per day? So we work with Dr. Katrine Tudor-Locke. She's the one that popularized that in the science literature. We came up with actual cutoffs for this. I'll show you that in a second. Okay, everybody understand what a distribution is? Any questions on that? Because if you don't understand that, we shouldn't move on. I felt like sometimes in the other class, at 376, there were students that came in that didn't understand what that was.
So is that going to the p-value?
I'm getting it. Okay, so I think the Garmin actually shows you a nice p-value. So now that we have this, see this yellow right here? That's me. And this is really important to look at because in terms of like devices like this, I like working with devices like this because they're objective. So when you collect data on physical activity, in the past it was always done by self-reporting. So I'm recording this, I'm talking about my mother-in-law, but my mother-in-law will say, I'm very active, I walk around the kitchen all day. And I say, I'm not active enough, because I think I'm in a competition with Sergeant Major. He's like flicking me to the side because I'm not in competition with him. But I'm looking at him going, I need to be more active. I'm not active enough. But this gives me an objective view of where I stand next to all Garmin users. And it says that I'm 99% higher than all Garmin users for steps per day. So that's pretty active. That's a proxy for the p-value. So that's a center, it's around 8,500. So in some of your work, I asked you to actually answer those questions. What is the center? What are these things? The shape looks sort of like a bell, but there's what we call a long left tail. So that's saying there is some variability down here. I kind of joke around that we as the United States are homo sedentarius. So there are people who are actually clocking 500 steps a day. 500 steps a day is shorter than Thayer Hall, like walking from one office to the other at the end of the hall. So.
Is that predicted, or do those people also have Garmin?
These are all just the data collected and put into the shape.
So they have Garmins, but just like stick.
What about like, because I know from my watch, I won't wear it like for the whole day.
So there could be some false positives in there. Yeah. No, this is actually real. I've seen it with actual data from the United States with actigraphs. The CDC put actigraphs on people, so this is actually right. When I want to compare, I compare to the null distribution. That shape that you're looking at I can take that as a proxy for the null distribution. If I didn't do an intervention, this is kind of where everybody stands. And I can ask, where do I stand? Am I different than other people? That's telling me I am. I'm 99% more active than all other Garmin users. So the p-value is what's to the right of me. What percentage of that entire data set's to the right of me? What percentage, what would you say is to the right of me?
1%.
1%, 0.01, that's p. It's called a one-sided, it's one-sided, right? I'm looking at what percentage of the population, how would I calculate that? I would take the total data set and see where I stand. And how many people are to the right? What percentage of the people are to the right? So I'm calculating the percent. That's what you're doing when you calculate the p-value. What do you think? Am I different? Would you say I'm different than the rest of the population that has Garmin's?
Oh,
Yeah. P is smaller than 0.05. That's the cutoff that we have for statistically significant. The p-value here is 0.01.
So if you're at like the 95%, or like if you're at like 94%, then the p it wouldn't be significant.
We say a borderline. Sometimes we say borderline. That's
Okay.
a rule of thumb, you know.
Right.
I can also ask other questions. Once I have this null distribution, I can ask other questions. This was a project I did with Major Adams, a former cadet. I don't know, Cadet Demos. I don't know if you guys knew him. You would have known him. He was in first year. Probably last year, I think. Graduated. We found that so when I talked to Dr. Tudor-Locke, and she said, okay, this 10 years ago we talked about it. I said, you know, that 10,000 steps per day, for what? You have to tell me what it is you're trying to make that cutoff for. Maybe it depends. And so one of the things you can ask, can I have you close your laptop? Thank you. One of the things you can say is like, how much would that cutoff have to be so I don't get diabetes? What's a minimum standard I have to have? These are minimum standards. And so we found it's about 5,000 steps per day. That's the minimum standard. If you're higher than that, you're less likely to have type 2 diabetes. If you're lower than that, you're more likely to have. That's like your how to not get an F. That's the standard, how to pass the class. And so I can ask, how much of that is in my Garmin data? What's this part of the thing? It looks like a fairly decent chunk. It's a bigger chunk than to the right of 99%, right? So if I just want to calculate the p-value here, that would be everything to the left of 5,000 steps. I calculate that and say, is that different than the rest of the United States using the Garmin? And I haven't calculated it, but you can imagine. You just imagine that bar being right here and asking what percentage of the total data is this part right here. And that would be the p-value for that case. Good? So the takeaway, the distribution you're looking at, all the purple, that's the null distribution for steps per day. That's what would happen if there was no change. It's my benchmark to compare everything to. This is where everyone in the US without an intervention staked out at. Is it clear? I asked that, and then on the exit interviews, I get something different. Is it clear, Day?
I'm still kind of confused.
Okay.
Wait, I thought the null distribution was not actual information. I thought it was infinite. It would be the distribution based off the hypothesis.
That's correct, but here we don't have, we actually have to get enough data
Is
to
this
make.
the alternative distribution?
No, this is the null distribution. The alternative hypothesis would be, am I different? I am different than the rest of the Garmin users. That's my alternative, right? These are all Garmin users. This is the null distribution for all Garmin users. If you have a large enough data set, it becomes closer to the theoretical.
If you were on average, then the alternative distribution would be equivalent with.
That's right. So if my yellow bar was right here, then it probably, being to the right of me is probably going to give me a not significant p-value.
So the null distribution is like, if, like that's what's expected for like now, like a week from now, a month from now.
Yes.
A week from now, if nothing happens.
Yes. Right. It's like what, this is the benchmark where everyone stands. Everyone's put their stake in the ground. This is what the shape looks like. Now I can start comparing me, you. I could start comparing people to where they look like on the null distribution.
So, I guess this is another way of looking at it maybe, but there's nothing like affecting the amount of steps per day? Is that why it's no distribution?
There's no intervention going on. It's the benchmark. Everything gets mapped to this and say, I ask myself, well, am I different? How about the people who are taking less than 5,000 steps a day? Are they different? So this is my benchmark of where I look at to say this is no different than anybody else, or it is different than everybody else. Does that make sense?
So the alternative is the second part.
The alternative is the second one. The alternative hypothesis is, the question, am I different?
Okay.
And you need some benchmark to look at that and say, am I different? Well, I have to look at everybody and ask, where do I fall in line with everybody?
I think I'm like asking the same question as her. I'm not like wrapping my head around like why this would be just like the regular distribution for your first.
I can say this is the regular distribution because it's a large amount of data. So when the larger the data set and more wide varying the data set, it is more of a reflection of what the true null distribution looks like. So this is actually a proxy for the null distribution. It's probably as good as I can get.
Okay.
Just like when we were simulating the coin flipping, it's not an actual random act of, when you do it, it's a pseudo-random thing. So you get this distribution that pops up on R, and it's a proxy for the null distribution. You can't ever exactly get it. So that's what but I need somewhere to benchmark it against. So then I can start looking around and saying, where do I fall? Where does someone else fall? There's the percentage of people who are taking 5,000 steps or less. I can start looking at that. I need something to compare it to. So the null distribution is what you compare it to. And ask, am I like everyone else or am I not? Got it? If I didn't own a garment, I do actually, I don't know why I said I don't. And if I wanted to look at USMA faculty, I'm comparing myself to a different population, USMA faculty. I'd have to get steps per day from USMA faculty. And their distribution, I would think, would be much different than what I'm looking at when I'm looking at everybody in the US. It may not be enough. That's the problem with us. Like sometimes when we collect, I got all your group spreads now, that might not be enough. So if I don't have enough, I can have R simulate for me what a null distribution may look like. So that's what R does for you. It's a simulation of what it would look like if I did some sample of people from West Point and then I ran that on R, it would give me that null distribution. So I can now benchmark myself against West Point faculty. So I have enough for Garmin users. That's a ton of data. I don't have enough for West Point. And even if I started sampling West Point, it wouldn't be enough. So that's when I use simulation to generate a null distribution because I need that benchmark. Got it? The third takeaway is, let's say I started a morning faculty run to rival the Commandant's PT. I got Dr. T's PT. I would expect to see a change in steps per day. I'd expect it. That's my alternative hypothesis, right? The null hypothesis is that Dr. T ran everybody up Washington Road and nothing changed. That's the null hypothesis. The alternative hypothesis is now I have faculty running and their steps per day should change they should be different than the standard at West Point. Darby?
So,
You got a frown.
I'm just going over it in my head right now.
Okay, so what would your actual hypothesis be?
So the H0 would be, probably I would use the mean. The mean would equal mean steps per day by West Point faculty. So my null hypothesis would be that nothing changed. I ran my intervention and everybody just stayed the same. Maybe they got tired after running in the morning and they sat on their desk all the rest of the day. You never know. The alternative hypothesis is mu does not equal that something changed. And in fact, I would say that they got more active, right? So I moved them from being somewhere here to over here. So I need a benchmark to say, where did they move from? Following? And that we write, so the confusing thing for me, because I'm not a statistician, I'm a mathematician. So when I started looking at stats, I'm like, why are they doing H0 first? It's the alternative I care about. Because H0 is setting up my benchmark. That's why they set it up first.
So I was confused by the null distribution, because the null hypothesis is saying like, if whatever you're expecting to happen doesn't actually happen, why do you have that full spread on the distribution? Then like you're saying like if I'm not different.
I have to know what I'm different from.
Okay.
I have my baseline. I have to know what I'm different from, right? So if I start out right now and say, am I different than what's my hypothesis? Probably not. I don't know. Maybe not. I don't know. So I need to know where everyone stands, so then I can compare myself to that benchmark.
So why is that? I guess I'm just stuck on the terminology. Like, why is that labeled as a null distribution?
Null distribution means no change. No. Nothing has changed. I haven't interfered with anything. This is where everyone stands.
Okay.
Right?
So then your actual is like after you start the run.
After I do the intervention, or benchmarking where I'm at compared to everyone else,
Okay.
right? My null hypothesis here would be my steps per day are like everyone else's.
Okay.
My alternative is I'm not like everyone else. I think I'm not like everybody else. That's why we think, well, why did that not come first? That's my hypothesis, alternative hypothesis, that I am different. Okay. So null means status quo. Alternative means the change, the different. A p-value is just the proportion of data that lies above the value you are at. Or below, right? If I was down here, like with the 5,000 steps per day, then I would look at the proportion of data that lies below 5,000 steps per day. And then we ask, is that p-value telling me I'm different or not? Well, you can just eyeball this and say, yeah, she's different. My family's been saying that for a while. You're different. I think I knew I was different in calc class, and I said, this stuff is awesome! And the rest of the class was like, no, this is not awesome. You're different.
So if you were at the 60th percentile, you would say that you're not different?
If not 60th percentile, if I'm at 60% of the data is below me,
Yeah.
probably not different.
Okay.
Yeah. The p-value would then be 0.4, right?
Yeah.
0.4 is above me.
Mhm.
That's not a significant p-value.
So what's a two-sided feedback?
You know, I have tons of examples of that, and for some reason it might be lack of sleep. I am not showing you my sleep distribution. I don't think I want to show you that. I don't want you to see where that yellow bar is going. But so I have tons of examples where it's two-sided, where it could be on the left edges away from the mean, right or left. So I'll bring one in the class where you can see it. They should have one in the book where it's two-sided.
Yeah, I just didn't like really grasp like the consume on that two-sided.
The two-sided means that you could end up here or here. Sometimes body mass index ends up there, like a likelihood of injuries versus body mass. If you start looking at body mass index, you could be low BMI or high BMI. But I'll come up with a good example so you can see it and it makes it real.
To calculate p-value for a double-sided, would you have to like add both sides?
Yeah, you have to put both your lines and say what proportion of the data is below here and above here. So you're just calculating what percentage of the data is beyond those two sides. All right, good? So that's how we say it. A statistically significant difference is what I'm detecting. Think of it as a signal. Am I detecting a signal? All right, got it? So when we did the apple juice experiment, let's just look back at that. So you guys were saying that this was confusing. That's what the feedback I got. A significant portion of you said that it was confusing. So when we generate this is the null distribution. 29%, that's the bar. 29% said that they preferred brand 1 over brand 2. So I look at this chunk of data right here, it's a one-sided test, and this percentage of data ended up being, turns out to be 3% of the class was below this line. So that's significant. A significant amount preferred brand 2 to brand 1. So I can detect a signal in preferences. It's not due just to random chance. Make sense? Well, that's hard to like calculate every time. So when we look at R, it actually does it for us. It counts what proportion of the data ended up here. It just does it for you. So you sum up the amount of data that ended up here and divide by the total sample size, you get a percent, and you end up with 3%. If you look at that line of code, that's exactly what it's doing. It's calculating the total proportion that ended up here divided by the total sample size. You got it, or are you just tired?
Oh, I got it.
We gotta stick a garment on you and look at your sleep data instead of my sleep data. I thought of showing that to you because it's an interesting distribution too, especially for older people. So if you go up to the 75-year-old, whoa, it's a really weird looking distribution. I remember my dad. He barely slept at night and he slept like naps in the day. And all right, let me test you. So that's a different distribution. I feel like we walk up a lot of stairs here. I had a med student staying with me for a while, and she'd come to the office, and she had to park down at the bottom and climb up the stairs from by Kuzku's garden and come up that, and she was huffing and puffing when she came in. So I took her to Arvin and I showed her the stairs, and I also told her there's no elevator. I know we're not supposed to lie, but I had a little fun. But we walk a lot of stairs here. So there I am. There's the yellow. What's the shape of this distribution? Do you think that it's, give you your cards if you want. Let's just do it by hand. Usually have you lift up a card. You want to do cards? Pass around. You should pick up a blue, pink, blue, purple, and yellow. I bet you these people that are doing 30 stairs are doing Stairmaster. Or whatever that thing is, or people walk up the stairs. John Casson used to always run those stairs, so I thought I'd try them. After 2, I felt dizzy.
In Arvin?
Yeah. The running it twice.
You gotta run up and then sprint to back, run down the sprint over and then
You want your teacher to finish the semester out, don't you?
I did that last semester. It was horrible. Oh my god.
What team were you on at this? I know boxing does those stairs a lot.
They need to, right? They're aerobic. There's an article today in the Times on aerobic versus strength. And I find it really interesting because they were saying aerobic is better for your metabolism. But I think some people walk away reading that and saying, oh, maybe I should just do aerobic and that running's okay. I always tell my sister, get down and do some hand release push-ups. 2, don't just run, because it helps with bones, it helps with your strength, it helps with fast problems. Do it all. And she's like, I don't have time for it. 2 minutes. Just do 2 minutes. You don't have 2 minutes? And then she told me I don't have the dedication to do that. My mom was saying that too, Mulliga, my sister just had a baby. She said, oh, she doesn't have time to exercise. 2 minutes worth of hand release push-ups. 2 minutes, that's all you need. Just do that. We run out of colors?
Yep.
All right, let's answer this one. Do the best you can. What do you guys think of this one? What's the shape of this? Long left tail, long right tail, or bell shape? Pink's going to be the substitute for the, that's correct. It's long right tail. That long tail has something to do with the variability. So it's telling you that you don't have a bell-shaped curve, you have more variability to the right. So there's a good chunk of Garmin users that are climbing lots of stairs, but it looks like the center might be around 6. The center is, we say, skewed. Is it skewed left, skewed right, or is this bell shape? I'm taking that's blue. That's correct. Skewed left. Skewed is, yeah, the center skewed to the left. So if you actually calculated the mean, where would you think the mean would lie?
Just at the beginning of the
The
descent.
mean would be over to the right. So why we say that, why that's important, is we like to explain things with one number. The mean is not a good representation of this data, because you can kind of see the bulk of people are hanging out around 6 floors. And it doesn't explain that variability that you've seen that long right tail. The variability of this distribution is high because there's a big bump to the left and the average is on the left, or is it low because there's a big bump to the left and the average is on the right, or it's high because the long tail to the right, the average is not a good representation of the data? 3. 3 is correct, the third one. So it would be like, you know, we were looking at data from faculty in the departments, and they said, oh, look at that horrible one from that one department. And it was just 2 people. One walked it, one sprinted it. So the mean is not a good representation of what really happened there. There's too much variability in that data set. And there's too much variability here for the mean to be a good representation. I'm surprised I'm not over here further, but I guess somebody's doing Stairmaster. Okay, so what I'd like to do